in this, then we don't have to redo this somewhere, sometime again. This helps at least. Right.
Okay, let's start. I didn't restart mine.
Did you? It's coming. Send. So looking at send Francis. Oh, Michael, here it is. I didn't send it. No worries. Michael, I'm sending as we speak. There you go. So Francis, import if you receive yours.
Yeah, I'm looking at it right now.
Okay, so
there it is.
As I said, it's actually much better to view it on my account and see why it's not showing up there. Actually, to look at it because you can make nice little comments at a place where there is something missing or where there's a bit of a mistake or it's thinking error or whatever is happening. Okay, so the first one, guys, you can't afford not to get 2 marks in here because energy, power, work, those are all energy related and they have no direction. They are scalars, while momentum has a velocity in, therefore it's a scalar. Force is acceleration in, therefore scalar, and acceleration is acceleration, hence vector. Sorry, I'm talking about vectors. So force, acceleration, and momentum, all vectors, while the energy related ones are not, they are scalars. Okay, so happy with it. And this is me scrolling with my mouse while I have the paper under the camera. Fantastic. Shows you where I am at this time. Right, so if we just consider quickly this little sphere that is dangling up here, we know the forces around it because it's balanced. There's my up thrust going up. I have a weight Fd, and I have my vertical component of that 10-N force. I'm going to mention it like that, FTV. All right. And I think most of you actually got this and you did really well at it. So you needed to see that because this sphere is floating, the forces around it are balanced. Okay. So they give you the radius of the sphere, they give you the density, and they also show that the weight of the sphere is that. Okay.
Oh, you're a jerk.
What?
I ignore that, sir. Ignore that. It's my sister.
Did she just say you're a joke?
Yep. Oh, God, mercy.
That's a recording of your sister, ladies and people. So
The show must go on. Please continue.
no worries. We're not going to listen to your personal.
Okay, I'm gonna beat this kid.
Don't do it on camera, Paul. Don't do it on camera. It's not worth it.
It's being recorded.
Oh yeah. Oh no. Sorry about that.
Right, okay, so using our volume of a sphere and using the density given to us, we can get the mass. If we have the mass, we can get our weight. And then half the problem is already solved. Listen, this is actually a lot of work for just 2 marks, but okay, we accept it being Cambridge and we accept we are there. And I think, as I said, none of you really had a problem with this. It was important that you recognize, by the way, that's part what the volume of a sphere is, and that you convert your centimeters to meter. And then Bob is your answer. Any questions on that?
No.
Right. So determine the upthrust, and again, we looked at the sphere, so we know that our upthrust is equal to the weight plus the vertical component of that tension.
So why is that?
What do you mean? Talking about?
I couldn't figure out exactly what upthrust is, because I only know upthrust as the difference between the pressure, like.
And you're right, it's the
top
difference in pressure, and you actually stated it correct, Francis. It's a difference in pressure on the top and the below surface. Right? So the difference between the pressure that that sphere is experiencing at that point and the difference that it's experiencing at the bottom. Due to that pressure, it's experiencing an upthrust. That's upthrust. And
okay.
the force actually pushing it up. All right?
Oh, okay. I couldn't think of how to explain that.
And that's why you would see you wouldn't score a mark in there. So it's actually
Yeah, so you even gave me a frowny face.
It did, because I couldn't do anything else. It's necessary to state that my resultant force is 0. And because my resultant force is 0, these forces must balance out. Okay, so now I've just calculated my weight as the 41 Newton. And then for my vertical component, it is the tension in my string times the sine of 75 degrees. Remember, looking at my triangle, bringing this back, it is this force. We always work in linear. So we needed to calculate that. So this side was opposite to 75, hence we're using sine. We calculated to be the 41 plus, and that calculates to 280. So my final answer is 321, but remember my data was given to 2 significant figures. So we also give our final answer to 2 significant figures. 2 significant figures. And now this is the question that you then said you didn't know how to explain it, Michael. You said explain the origin of this upthrust. Well, it's the difference in pressure between the top and the bottom surface, and you can say of the sphere in there. Let me just write it in a bit of detail, then you can see it. It's there. Right. So if you said, and I think Francis, you spoke about the pressure of water and the pressure of the air, something like that. I'm not quite convinced. I think you said something about that, and that is true. All right, that is 100% true. That is also given as an alternative answer in the memo. So very good. Right, definitions, guys. Inexcusable, I think all of you got it. So what is velocity? Velocity is the rate of change of displacement. Rate of change. Also, if you said, well, it's displacement over changing time, something like that, that is fine. Or displacement over the time. Please don't tell me it's speed in a given direction, not the proper definition they are. Okay, not the proper definition. All right, let's move on to our next question. Oh, sorry, I actually have it at the bottom there. It's about the car that travels up a slope as shown. The car has a specific mass, and it travels at constant speed. That constant speed is important. The speed is at 9 meters per second squared. If it's constant speed, we know that F res is 0 Newton. So there's no resultant force. There's also no acceleration. Acceleration is 0. right? The car's engine exerts a specific force, kilonewton, 2 kilonewton up the slope. There's a resistor force due to the friction and air friction, all right? And the variation of that resistor force, the speed of the car is shown. So this is very nice. They give us this graph. And they say, right, state and explain whether the car is in equilibrium as it moves up the slope. You guys answered this really nice, right? And 2 marks just because you did the effort of reading the paragraph. Since my car is moving at a constant velocity, my resultant force is 0, so the car is in equilibrium. Right. So you needed to think of with that last bit that the car is in equilibrium because it says state and explain whether the car is in equilibrium. So yes, the car is in equilibrium, constant velocity, so resultant force is 0. You will score the marks for that. All right. So let's quickly look at the next one. So consider the forces acting along the slope. And there's my little picture. Use the data from your graph to determine the component weight of the car that acts down the slope. You know, and this was such a nice one to do again, because as I said, with mechanics draw, we've got the force of the engine. That's at 2000 Newton working up. The question asks to calculate FG parallel. And then from your graph, you could go and calculate or read down the frictional force, that FD. So I go to my graph at 9 meters per second, going in and reading off is 0.4 kilonewton, so it's equal to 400 Newton. Right? So if I have that now, what should be FG? Well, it's the 2000, and I can write it down. FG parallel is equal to my 2000 minus 400, and it gives me my 1600 Newton. Right? If, as I go along and there are questions, speak up, it's good. Otherwise, I expect or accept that you guys are okay with it, right? So, show that the power output of the car is that 18,000 watt. Well, we know the formula P equals force times velocity. It's the output, so whatever force the car is producing, the 2 kilonewton, times the constant velocity that it's traveling at, and it gives you a power of 18,000 watt, which is, of course, 1.8 times 10 to the power 4 watt. So yes, we showed it. It is equal to that. They've changed the question slightly. They say, well, listen, the car now travels along horizontal ground. So immediately when it travels along horizontal ground, we know what? We know that the weight component is no longer there. So there's no incline. If there's no incline, the weight component is gone. So I'm just mentioning it here. So no incline. Therefore, if G parallel is equal to 0 Newton. Also, what we can...
By the weight component...
Yeah.
Sorry, by the weight component, do you mean there's still the normal FG? Is it just this, like,
Exactly.
the X and Y component?
Yes, because now we're on a straight road. FG is going down while my motion is forward. So there's no longer a component. So the horizontal component of this is going to be 0. Do you agree?
Okay. Yes.
So it's no longer there. So now it's just the engine of the car, and it is the drag force, the resistance, air resistance that's playing against it. Only those two forces. Right? They give us more information. They say that the car's maintaining that output. So power stays 18,000, right? But we know because my speed is increased, my drag force is also increased. And I know my drag force by reading it down from my graph, and I get 660 Newton. Just to show you again, I use a pen or a pencil and I dotted it. So because your examiner is going to see your graph. So if you make a mistake by reading it off, perhaps they are lenient if you show where you read it. So now I have my drag force. I can go and calculate the force produced by my engine, because that's going to be different now because of the weight component not being there. I have my 18,000 for my power. I know my velocity, and I get my force of my engine being 1,200 now. So when I write that in, now suddenly my force of my engine is 1,200 Newton, and my drag force is the 660 Newton. So immediately, forces are no longer balanced, there is acceleration. And that's the acceleration that the question asked us to calculate. We know that my resultant force can be calculated by using Newton's second law. So if res equals mass times acceleration, my resultant force is the sum of my forces. And I know, well, positive direction is as it moves in the direction of the engine. My mass is 850. I can get my acceleration. Acceleration is 0.64 meters per second squared. So this was a tough question if we consider the paper. But again, I think all of you did really well in this question. Any questions that you guys have? Right, let's look at our, I think it's our second last question that we have in here. We have this ball that's being projected off of a table. And I think when we did this topic, we actually looked at a question similar to, if not to this question. What you need to remember is in a question like dealing with projectile motion, we know gravity works down, and this is your only acceleration, your only net force experiencing. There's no net force working in the horizontal. That means my horizontal velocity will stay constant. And it's this fact that helps you to calculate the time taken for the ball to fall from A to B. Because if you have a displacement and you have a constant velocity of 1.1, we can calculate the time. So we use our very basic of formulas where we say, well, the velocity or speed of the ball, distance over time. So time is equal to 0.43 divided by 1.1, and it gives me 0.39 seconds. So that's my time. For II, use your answer in BI to determine the height of the table. So now we at least know the time that it takes for this ball to fall down. That's at 0.39. We know gravitational acceleration for this is 9.81 meters per second squared. I'm going to write in the time that we just calculated, So delta t is 0.39 seconds. We also know, because it starts with a horizontal velocity there, my vertical initial, so u, my vertical is 0 meters per second. I want to calculate, in essence, delta y, the displacement. So I'm going to use equations of motion. My equation of motion that I used is equals ut plus a half gt squared. Is this whole term is 0 plus a half 9.81. This is 0.39 squared. And we get that the height of the table is 0.75 meters. Right. And none of you had an issue with that. All good. Let's look at our graphs. Now, they say the ball leaves the table at time 0, and for the motion between A and B, sketch the variation of, with the variation, or show that the variation of time of acceleration A of the ball. Well, remember, A is my gravitational acceleration. So A is my G. And because we are such a short distance above the Earth's surface, G stays constant. It is 9.81. It doesn't change. It doesn't change for us. Please always use a ruler and draw your line. So it's a straight horizontal line. It stays constant. For my displacement, my vertical displacement component, so as I move down, what happens to my velocity? My velocity starts at 0 and picks up. Do you agree? It increases as I move down, as I fall, right? So because there's an increase in velocity, and I know when I have a displacement time graph, the gradient of this line, and I'm just looking for, sorry for this. This is the only thing I can get. I don't know what happened to my ruler. I have a band 8 master here, so I'm going to use that. The gradient of this curve indicates velocity. Okay, that's improvisation. I mean, if you can use band 8 to do science, you know, there's my band 8, then, you know, that just shows it's everything's okay. So displacement time graph, gradient is velocity, velocity is increasing, but very important, you cannot go into a constant speed. It's not reaching terminal velocity, okay? So make sure this does not go into a constant gradient, right? It must show a curvature the whole time. Otherwise, you will lose the mark. So it's starting and it curves and it curves and it curves and it curves and it curves, and then you stop. Then one question that some of you had some problems with. They say the mass of the ball that is projected, a ball with greater mass is projected from the table with the same velocity as the ball in A. Air resistance is still negligible. Now, air resistance could affect this because of surface effect, but for the rest, there is no effect due to the increase of mass. Why? Well, my acceleration, so I'm setting no effect. Why? Because my acceleration is unchanged. Remember, we're working with G. I'm just saying, you're working with G as 9.81 meters per second squared. That's what you're working with. It's mass independent. Think of your equations of motion. Nowhere would you take mass into consideration to calculate the time in there. It is your velocity and its acceleration that you take. So stating it's mass independent will also, it's mass so it would have been slightly different in resistance, right? Because air resistance will play a role in there, and you will reach terminal velocity, well, slightly bit later, most probably. Okay, let's look at displacement and acceleration definitions. Right? Displacement, it's the distance moved in a specific direction from a point, and acceleration is the rate of change in velocity. You can write it in like that as well. So it's distance moved in a section from a point, and acceleration is the rate of change in velocity. So you could have talked about velocity per time unit, right? Per unit time, that would also have sufficed. Right, let's move over to our paraglider. A man wearing a wingsuit glides through a constant velocity of 47 meters per second and an angle of 24 degrees to the horizontal. Right? The path of the man is shown. So very nice, very nice. Again, it is a constant velocity, so we know the forces around it is balanced, and that is also my answer to the first question. With reference to motion, state and explain whether it's in equilibrium. So C is in equilibrium because the velocity is constant. That turned out bad. No resultant force. So in right. Sorry. Oh, there we go. Back. Right. So also important to note, they said that takes 2.8 minutes. Already, if you see that converted to seconds, it's 186 seconds. Because now it comes in, they ask you, show that the difference in height h between the points A and B is 3,200 meters. All right. So we want, going back to our sketch, we want h. We can determine A and B because we have the speed and we have the time that it takes. So if we have that, we can calculate the distance. A, B. And that is the 47 times the 168, and it gives me 7896 meters. Keep it like that, don't round it now. Then, because we sit with a 90-degree triangle, we can use trigonometry. It's the opposite side. We have the hypotenuse, so we use the sine 24. And it's h7896, and we get that h is 3211 meters, which means 3,200 meters, as they asked us to show. Right. For the motion of the man from A to B, determine the decreased gravitational potential energy. Yes, you got this one as well. Loss in EP equals mg delta h. That's 85. The mass gravitational acceleration. And then we use the 3,200 because they asked us to show it is that. And we get to 2.6 times 10 to the power 6. Right. I see we've got a minute and a half.
Michael, can you hear him?
Yeah,
There we go.
he's frozen. Oh, there we go.
I'm back. Sorry, I lost it just for a moment there. Listen, guys, I'm going to talk you through this. We've got a minute remaining. So,
He's
very
frozen
important.
again.
Are you guys, am I frozen? Can you hear me?
You're back.
No, you're unfrozen.
Am I unfrozen? Okay. Geez, I didn't know there's something like that. Listen, there's a minute left. Have a look at this. EK is constant in there because they say it's constant velocity. So the loss due to, or loss in potential energy is equal to the work done. And it's equal to the work done against friction. And this is how we can calculate it. So work done against friction, all right, will give me the force of friction. We have the distance, remember it's the force and the distance, and we can calculate it to 338. With the last question, with pressure, there weren't any issues. You guys